Good morning, everybody. Morning. My name is Tom Cherryhomes. I am, amongst other things, a computing archaeologist, and this particular talk is the result of an interesting set of opportunities, namely the development tools that Atari used for developing their coin-op arcade games, like Centipede, Missile Command, etc., were found, and they were preserved by Al Casso over at bitservers.org. And I've taken these tools and put them together to show the whole process here and what of literally using these tools to do game development on, and what was actually and how things were kind of done within the limits of being able, what I can do with my presentation here of how games were being developed at Atari. So what are we talking about here? We're talking about coin-operated arcade games. These are games that you walk up to, drop a quarter into, you play your game over, you're done, insert another quarter, or you walk away. Well, these games were computers in and of themselves. They were bespoke computers that were designed specifically to play the given game in question. They consisted of a microprocessor, in this case, the 6502 microprocessor here. They consisted of a number of chips that implemented the graphics subsystem for the arcade game, which for Atari games during this particular point in time that we're talking about, which is from 1978 to 1983 or so, we're talking about games that have background tiles, that have movable objects, which they called stamps. Atari was that was the nomenclature that was used at Atari at the time, and you're running through the game logic to take and display all of these things and create a visceral game experience that lasts on average, anywhere from 3 to 5 minutes. Insert another coin. Because these were custom-made machines, and because these machines were not intended to do the software development on themselves, you had to use another machine to do the development on. So you needed some sort of a development system. In this case, Atari used as one of their primary development systems in coin-op a PDP-1120. This was the very first of the PDP-11 line from Digital Equipment Corporation. It's a 16-bit mini-computer. And for the time, it was considered to be a very decent piece of kit to get serious work done on. The particular machine that Atari used had 32 kilowords, that is 32,768 16-bit words of memory. But it also had a number of storage devices which were used to get things into the system and out of the system. And the most common bits, and what we're actually going to be using here in emulation, are the three RK05 2.5 megabyte cartridge drives. These were very common, especially in the mid-1970s. They used a very standardized cartridge format that was shared by IBM, it was shared by Diablo, and a handful of other cartridge drive manufacturers to basically do all of your medium storage capacity needs at the time. Each cartridge could store 2.5 megabytes each. We also have an RX-01 floppy disk here that's being used for backup and storage of small artifacts. Each RX-01 contained 2 disk drives. Each of those disk drives could store 256 kilobyte floppies each. And so it just so happened that the RX-01 used the standard IBM 3740 floppy disk format. But the system that's going to be burning the EEPROMs, so to speak, once we're done assembling all of this, has none of that. All it has is a paper tape reader. And paper tape, for those of you who've never seen paper tape, it's literally just a long piece of paper. In the case of Digital Equipment Corporation, it's fan folded, and you can see it right here inside the reader. And it's got holes punched in it, which correspond to the individual bits of data, all just 8 bits across, with a center line for basically keeping everything aligned. And we're going to be using the paper tape reader once we've assembled and linked all of our stuff to ferry this over to the EEPROM station to make the EEPROMs so that we can take and display everything. Now, at Atari, they used a Model 33 teletype as the primary console for the PDP-1120. We're going to do things a little bit nicer here. I have a VT100 hooked up. And for those of you who have not seen a VT100, this is a very nice data terminal from DEC. It was produced from 1978 until about 1984, 1985. And provides the keyboard and the display that we're going to use for our console. Our operating system that the DEC PDP-11 is going to be running is a copy of RT11 version 4. This is a single user operating system. It has a lot of common roots, similarities on other PDP systems, the PDP-8, OS-8, that sort of thing. Run one program at a time, wait for it to finish, do the next one. And a lot of operating systems after RT11 took common heritage from it. CP/M, for example, MS-DOS, for example. You'll see some interesting similarities in the commands if you're familiar with those operating systems. We also have what is essentially a black box. This was a term used at Atari to indicate a development system. And it basically consists of an in-circuit emulator that's plugging into that Centipede board that we saw earlier. And it takes the paper tape input that we have here, throws it into its internal memory, and overrides the CPU instructions and everything to actually take and send that game data over to the final board. So, we're going to have to basically, I made a note here, basically using paper tape is an example of the improvisation that's needed by old school developers, because a lot of what we had to do here, they had to make their own tools for all this stuff to work. And just as an example here, the assembler that we're going to be using is called Macro 65. And it's called Macro 65 because what Atari Coin-Op literally did was they took the Macro 11 assembler that was used to write PDP-11 software normally, and they transmogrified it to output 6502 code. Think about that for a second. Not only did they do that, but they took the linker that's normally used, linker 11 on under RT11, and they transmogrified that to output 8-bit binaries.
The Indian is different too, isn't it?
Huh?
The Indian is
Yes. All of the above. It's just the amount of weird transmogrification that they had to do was nothing short of insane. And in point of fact, I have links at the end of the presentation here, so you guys can go onto the GitHub and you can see the tools that they used and how they modified them for these purposes. So for the first thing, what we're actually going to do, our goal for this presentation is to take a copy of Centipede in source code form, load it up into the system here, make one change to the code, assemble the resulting code, link the resulting code to get our EEPROMs out, and then put those into our development system. And since I don't have a Centipede board and a screen here to show, I'm going to use MAME. I hope that's okay. So we're going to go ahead and start here by booting ourselves into RT11 to edit the code. And for this, we're going to use the excellent SimH emulator to do this. And just so you guys can see the configuration that we're actually using here, we have an 1120 set up with 32 kilowords of memory, We have a system drive over on the first RK05. The RK1 will hold our source code that we're assembling, and RK2 will hold the binary artifacts that we output to the paper tape punch. We make sure that all those are set to write enabled, and then we take and boot in. So I'm saving us one other thing that's different here is I'm saving us the pain of running this at real speed. This is being run much faster than an actual PDP-11, and if we were to do the entire process of assembling and linking all of this together, we would be sitting here for 15 to 20 minutes doing absolutely nothing while this thing waited. At this point, we're booted into RT11, and it's waiting for a command here. The dot prompt here indicates that we're waiting for a command. We can do a directory on our system drive to see kind of what's here. And for all intents and purposes, this is a pretty standard RT11 installation. And we'll actually see one of the nice things that you just don't get anymore are the source codes for all the various little bits of the operating system, for all the different device drivers and everything that you need to make device drivers, to make new bits and pieces for the operating system, because these people were using these machines to get things done, and they needed this to build the custom things that they needed. We have down here at the bottom here, we have our macro assemblers, Mac65, Mac68, and our LinkM that we're actually going to be using to do this. But first, we're going to be editing the code. For that, we look on disk 1, we can see we can see all of our Mac source code here. And we're going to be using, because we have this nice VT100, we're going to be using the keyboard editor. Edit/KED, and we will edit SYN-IR2, which contains the bits and pieces that we want to change here. Oop. It helps if I actually put an extender. And we're now inside of DEC's full screen editor, which they called keyboard editor here. And because, well, VT100 is fairly universal here, I can actually still use this editor as it is, even on this particular terminal program. And if we actually dig down a little bit, we can see that this is the original source code for revision 2 of Centipede with all the comments. So you can dig through and see what they were thinking about at this particular point in time. You can see the individual labels on the left-hand side, followed by the instructions and their opcode fields for each of the parameters, and you can see all the little comments over on the right-hand side. The place that we're actually going to modify here is over here in the messages section. And we're just going to take and do a little. We'll do that. Sure, why not? So now that we've done that, we can take and save our changes. One thing I do not have on this keyboard is the right-hand numeric keypad, which is used for all the commands. Thankfully, I have them all written down right here, all the escape sequences to redo those key presses. So let's do each one of these in sequence. We need to go ahead and get into command mode, escape OP to do the gold command. Nothing happens. You don't indicate that anything's happened here. But when we do the next command, which is keypad 7, we'll see that we've now gone into command mode. We can then do our exit. And then we can't hit return. We have to hit the keypad enter. If I hit return here, it will abort the command because I obviously typed it wrong. Escape OM, save the file, and we're done. At this point now, we can go in and we'll do a couple of things a little bit of some file management to make managing this a little bit easier. I'm going to assign the default drive, which is called DK and RT11, to RK1, so it deals with our source code. And we use the assign command for that. Okay. Now, if we actually take a look, if I do a directory, we'll see what's here on this drive right here. This COM file is not a binary file, but this is what RT11 called its batch files. These were command files. Let's take a look inside of one of them. You can see all of the bits and pieces that I'm about to type out, where we're going to take and do the resulting assembly, which will create the relocatable object files, the resulting links, and then using the tool, the one tool that wasn't on here called image file, which takes the file that's produced by the linker and cuts it up to fit onto the EPROMs. Thankfully, we can use DD for that in Unix once we bring it over to our development system. So let's go ahead and do that. We'll run Max65. And even though I've changed the default drive over to my DK1, since Max65 is on my system drive, it'll just load the software here. At this point, we start entering commands to do the assembly. And the way that this command line is parsed, it's just like if you've used pip under CP/M, similar operating systems. The first parameter is the destination, and the second part is the source that makes up that destination. We compile that. Okay, no errors detected. We have just enough memory to do that, it looks like. We assemble the bits and pieces. Each one of these is a few minutes at a time, but thanks to the miracle of modern emulation, this happens much faster. Thank God. The last file here is basically just a dump of all of the picture data that's in the ROMs that are used for the graphics, for the stamps, and the background tiles. And there is also what is called a sync prom. And if you've ever seen the sequencer prom for a Disk 2 controller, where it's a finite state machine for given inputs, give these outputs, it's the same thing, spread across a 256 byte prom. So now we're done there. We can take and get out of the assembler by pressing Control-C, and we can see what we've actually created here. Now we have a set of object files. These files are not complete yet. They've been assembled, but all of the addresses inside these object files are relative to the start of each of these object files. And some of them have external references that haven't been resolved that point to other parts, these other object files. To resolve that, we need to take and use the linker. And the linker's whole purpose is to take each of these object files and to sequence them so that they appear contiguous inside of memory. And once that's done, it can take and then resolve those relative addresses into absolute addresses on the target machine. Run linkm. And the command line is pretty much the same here. You have a destination equals built from the source material here. So we're building centi2.sav. This will be a save file because it will be an absolute memory image of what's being output from this linker. And it's made up of centi2, centir2, cents2. No errors, so it just drops us back. Same here. Same here. Great. Now we have our main ROM here, which is Centi2. We have our picture ROM, which is Cinpic, and we have our sync PROM right here, Sync2. Those 3 bits and pieces, and they're now living on drive 2. It also created, among other things, these map files, which are denoted by the .xx. If we look at Centi2.xx, we can see a whole bunch of symbols that it created for the target image and where they actually exist, how and what the linker resolved these symbols to. These are addresses in the 6502 space. We also see where everything stops, which is at the 16K boundary here. Now that we've got everything built, now we have to send this over to our black box. And the way that we're going to do this here, recall that our black box takes paper tape in. Well, thankfully, our PDP-11 has a paper tape punch. So I will take exit. I'll walk over to the paper tape punch real quick, and I will attach a new roll of paper tape ready to go. It's nice and blank. We can continue. And we will copy Centipede over to the paper tape. Now it's just taken and punched that paper tape for us that we can now use. And I'll do the same for the other 2 files. PTP, synpic.save. And the sync PROM. Okay, we can do this because the paper tape output is 8 bits long. It's safe. Each row is 8 bits and can safely encode the binary data onto that paper tape. We don't have to worry about encoding it or switching it around, making it work so that it's ASCII compliant. It's just there and it works. So, fine. Now we carry the paper tape over to the development box. Okay, great. We need to do a little bit of work here. Let's exit the RT11 environment completely. And let's have a look at save files that have been created. We have our main binary here, which is 16 kilobytes exactly. We have 4K of picture data and the sync PROM, which is a bit bigger than it needs to be, but it's fine because the first 256 bytes contain the requisite data. The machine will be fine with it. If we actually take a look at Centi2, we'll notice that the first few K of the file are completely blank. Again, recall that I said that the linker creates an absolute memory image of how things are going to sit in the address space. On the Centipede memory map, the top part of memory is completely not used by the main system. It's not used by the program code. So it's completely empty. We don't need it, so we need to take and slice it off so that we can take and make the EPROMs. So we will use our paper tape cutter to do just that. So if we look at the line here, we take Centi2 input and we output this to our development system, and it just will happen to have the correct EEPROM number and position on the board. So first number here is the serial number, then the chip number, then followed by its grid position on the board. If you look at the Centipede board, you'll see letters and numbers that correspond like a grid on a map. This is where the chip goes. We need to do this for the remainder of those, and I will just pull those over like this and do them all at once. If it will let me, come on. Okay, sliced all those files up. They're now sitting in the development system, and we can now go to our black box and start everything up. Run it in debug mode, because that's essentially what would happen here. In Atari's case, this would literally be an in-circuit emulator with a few basic debugging functions like being able to stop and trace the processor, but you would also be attached to an HP1611A logic analyzer so that you could see the output. Oh, Centipede 2. Here we go. Okay, so far so good. Cold start's indicating 3BOD, which is correct. And you'll see almost immediately right here that we do what we do in all 6502 code. We go ahead, clear decimal mode, set our stack pointer up. Everything looks good. So if we're familiar with this looks good, this looks sane. Now let's start it. We start it, it's running, and oop, I did the game over. I should have done the high scores. Oops, I could do that actually. Well, actually, let's see what happens. Yeah, fine. We'll go ahead and just play it. Yeah, fine. Come on. Run through it real quick. Some of you might actually be wondering, you know that there are, yeah, there we are. Hello, VCF. So that's literally, yeah, that's the entirety of my presentation here. I've left a few minutes here. If anybody has any questions, I can answer. Yes?
I'm Matt McCullough. I live in Fort Worth. I've worked on arcade games a bit. In the late 80s, I worked at Six Flags repairing the arcade games. And I had a little PC-based EEPROM reader and programmer, but yeah. I didn't know anything about programming these things from scratch. But the text editor did allow you to skim through all these hex codes and locate ASCII data.
Yes.
And you could see these terms like high scores, player 1, player 2. And we experimented for a time with reprogramming some games to show the words tokens only on the screen.
Yes.
Not all games would let us do that.
No.
Because sometimes they would run a check.
Yes, and I can explain here. I'll take that one here. That's a very important point, and Atari did this. Atari did this a lot. Atari has running checksums for all sorts of strings inside of the game. One of the biggest, you'll notice there's a copyright string down here at the bottom. If you change that and don't alter the checksum inside the code, game will crash. Same with a number of other strings inside the program here. We just happened to change one of the strings that you actually could take and change here just fine. And there's actually it's calculated, so as long as you keep everything aligned appropriately, yeah, and we've got the source code here, so it's actually able to assemble everything where it needs to go. It will work. Yes.
This might be a whole second talk, so I apologize, but can you talk about the archaeology? How was the source, and more importantly, how were these tools found?
Two things. So these two things were found. The funny thing, computing archaeology is so strange because we find things in bursts, in small bits and pieces at different times. The source code itself was basically found and given to a GitHub repository called Historical Source. And Historical Source has all of these things that have been gathered from printouts, such as printouts that came from Atari, or they came from RK05 backup disks, they came from RX01 backup disks, etc. And they've all found their way into these individual GitHub repositories. And one of these GitHub repositories just happens to be Centipede. So you can come in here and you can use GitHub's tools to take and cross-reference and see how, and see all of these things in these historical contexts. Now, as far as the development tools are concerned, another individual in this community, a man named Al Casso, a former Apple engineer, basically worked all over Silicon Valley for decades, started a site called bitsavers.org. And Bitsavers is absolutely wonderful for archiving all of these disparate pieces of computing history. Not just, but it's basically split into two pieces. You have a software archive, which contains, among other things, the tools that we found here. Basically, Al tapped me on the shoulder and said, here, I found the development tools. Maybe you can do something with them. And I was able to put this talk together as a result. But there's stuff for all of these ancient machines, software and manuals and documentation, so that we can understand how these machines work. And for those of us who are lucky enough to have them, to keep them running. Anybody else?
So were the tools under Atari? Or were they...
Yes. Tools are under Atari. As a matter of fact, yeah, Atari tools. They're spread out across a number of RX01 disks, and we had to take and carefully piece everything back together. But now...
A question. I worked on a number of Centipede motherboards, and Atari had like two different versions of software for it. Do you know what the differences were?
Atari actually had 4 revisions of Centipede. We just saw revision 2, and mostly the differences between revisions boiled down to either bug fixes that were found during playtesting, and as well as tweaks to various algorithms to tighten up gameplay as they were found in game testing. And you can actually, because we have all of those revisions of Centipede are actually archived, you can look through them and you can compare them to see what they changed. It's awesome. And yeah, actually, if we dig through a little bit, I'll go ahead and put this up here for those who want to see it here. You can take the picture. You can ask me for a copy of the talk. It's up on GitHub, but you can go to the CoinOp assembler repository here, and you.
Could you wait to that original screen, please?
Yes.
Thank you.
And you can pick up a copy of this, pull it in, load it into RT11, and you can hack on it yourself. I put this all together in a nice little GitHub here, along with this very talk and all of its source material, so you can reference that as well. Isn't it?
There was an article I saw online a couple of years ago where one of the designers on an earlier Atari game called Starship One.
Ron Milner?
Yeah, he remembered that he had put an Easter egg in the game.
Hi, Ron.
But
Yes.
He didn't remember how to trigger it.
Yes, we had found how to, yeah. Oh, yeah. That was an interesting little excursion.
So were those CRC checks and things, where they prevent the Easter egg thing? I mean, obviously it's copyright.
Yeah.
You got a copyright thing, right? But did were they more of a let's prevent the Easter egg kind of thing getting shoved in there, or I mean, I guess because I'm a developer, I'm developing the thing, I can do my own CRC,
No,
right?
the CRC checks were primarily there to prevent bootleggers from stripping out the copyright and putting them into quote unquote unauthorized cabinets.
For the longest time, right? Because you look at the Ready Player One, brought that to light for most people, although I'm sure everybody in this room already knew it. For the longest time, they didn't want the developers known.
No, they didn't. At Atari especially.
Yeah, but the Easter eggs were done on the Atari
Yes.
side, and so you already have the CRC
Yes.
generation. It's on
Yeah,
the good side.
all of that gets calculated. All of that gets calculated during assembly, and so all that matches up.
When you have the tools that doesn't. When you don't have the tools, is when you're a bootlegger.
Yes, there are some. Yeah, exactly. And I will actually point out too, as well, the one thing that I wish we could actually show were tools like the sketch program that was used to actually take and do the bitmap graphic stuff.
That's a whole different.
That's a whole different thing. It has not been found, and it ran on a very custom chunk of hardware. So it would be interesting to see, if we could find it, then we could actually have a chance at actually taking and making it run. That would be fun. I also want to take and thank another person here who worked at Atari, Dave Shepard, who basically was the head of coin op engineer, who helped take and make a good number of these tools, the Mac tools, the LinkM transmogrifications, etc. His work and his advice actually helped make this talk possible as well.
Yeah, but you know, Microsoft did a similar thing with a different deck series, but to
Yes.
Microsoft Basic, they hijacked
PDP-10, yeah, the PDP-10 macros. Yes, I would actually love to see that original macro set.
Yeah, because they had it to where you could compile the code for 8080.
Yes.
You could compile the code for C02.
Yeah.
You could compile the code to run directly on their PDP-10.
Yes, absolutely.
Yeah.
So.
Which is really clever.
Yeah.
So did you have to figure out the steps to build
Yes.
tools?
Yeah. It was a good thing that I was familiar enough with how macro 11 worked and how link worked, that it was almost just a straight translation over. It just happened to work. The issue that we ran into initially was finding the right copy of LinkM that didn't have. There were two copies of LinkM that we found, and one of them was corrupt at the end that we had to take, and we found a good copy that worked. Once we did, everything fell into place and started working. And it's really amazing. I love the fact that we can basically take the source code that has been archived and build a copy of it from beginning to end. That hasn't been possible until now.
Was it this project that had you found the similar syntax carried over to the Atari macro assembler?
That's a whole different talk. And no, this assembler uses a totally different syntax from Atari macro assembler. For those that don't know, Atari macro assembler was the assembler that Atari used in the home computer division to write their Atari 8-bit titles. Totally different assembler, totally different beast. This is its own thing. And nobody else used it but Coinot. And only for a short time, because by 1984 they had moved over to the VAX and they had a whole new set of tools that were written in C. Have not found those yet. I think, well, maybe Dave, I'll have to check again, but yeah. Anyway.
Do we have the source code for most of the arcade games, or just a few?
Quite a few of them, actually. Go digging through the historical source. You will be surprised, given that a certain company tends to be litigiously trigger happy. I'm not going to mention too much. In fact, I think I may have revealed too much already. Anybody got a way I can get to Mexico? So that's pretty much it, guys. I appreciate your time.